almost like an extended warm-up here. This is going to get us ready for related, right? So go ahead and find dy dx for this equation right here. Just for fun, I'm going to make this 100. It shouldn't change your derivative, but I want to illustrate a point with it later. Okay, turn your neighbor. What is dy dx? Okay, so remember when we're doing a derivative here, we do the derivative of each thing normally. So for both, we're using the power rule. When we use it on x, it's just 2x. When we use it on y, it's still 2y. But then we also add on this dy dx at the end of it. So we still do the derivative normally. The dy dx doesn't replace the y, it's just next to it there. Basically, it represents doing the chain rule. So the derivative of the outside here is like the squared power, and then the inside function is y. And so we do 2y on the outside, and then this represents the derivative of y. We do that because usually we have equations that are solved as y equals. So then we solve, and we should get negative x over y. Okay. So what dy dx represents? Dy dx is the rate at which y is changing compared to the rate at which x is changing. I'm going to explain that more. Okay, so let me show you what that might mean in this context. Like, I know that we know that that sentence is true, but let me just illustrate it a little bit, trying to make it a little more tangible, because it can be pretty abstract. So x squared plus y squared equals 100 could represent the equation of a circle with a radius of what? 10, yes. So let's just pretend, oh wait, I think I can do like, hey, look at that, that's fun. Okay, so we have a radius of 10. There's negative 10, there's negative 10. Okay, so an example of a point that would work would be if x equals 6 and y equals 8. We could think of this like from geometry, right? 6 squared plus 8 squared equals 10 squared. It's a 6, 8, 10 triangle. It's a multiple of 3, 4, 5. So that's a point that works. As we go around this circle, let's say we're going counterclockwise, what's happening is x is getting smaller and y is getting bigger, but they're getting bigger and smaller in a way that still makes this true. Like x can't suddenly become 4 and y equals 10, because that won't make this equation true. Like, it's restricted to the shape of this circle. They get into a bunch of weird decimal points. I guess I could pull this up on Desmos and we could trace, but like as x gets smaller, y has to get bigger by a certain amount, but it's a very specific amount to make sure that we're still on this circle. We can keep going until we get to a similar point, -6, 8, but it's basically x has shrunk by 12 and y has stayed the same, but they're growing in relationship to each other. As we keep going here, x continues to shrink, it gets more negative, y is also shrinking, and we could get to a point here that's -8, 6, which still works with a lot of other decimal points in between. So basically x and y are changing, but they're fixed to this relationship. And so what dy dx, or -x over y, this right here, what it describes is, okay, we can figure out how much will x change, or sorry, how much will y change if x changes this much. Or it tells us, another way to think of that is the slope of a tangent line. Y goes up this much as x goes over this much. It's rise over run. So it's them changing in relationship to each other. That's what dy dx represents. But we can still take derivatives that don't give us dy dx, that actually tell us other things. We can take derivatives with respect to time. And we'll do it for the same function here. So what that looks like is we still would follow the same process here, except when we get to x, we're going to write 2x dx dt. What dx dt represents is the rate at which x is changing over time. And so that might be in like meters per second or miles per hour or something like that. And so what that means is when we continue taking the derivative of this function, we are going to do that for y as well. It's going to be 2y dy dt. And of course it still equals 0. And so dy dt represents the same thing. It's how is y changing over time as time passes. So the two things are still related to each other. X and y are still related. They're still making this circle shape. There's still only a certain values that they could be to make this equation work. It's all those points on the circle. But now what we're imagining is like a dot basically going around this circle as time passes. And we're kind of measuring, okay, as we go around the circle, let me go back to my circle here. As we go around the circle, as I do that, x and y are changing. And the speed at which I go around the circle, like as I go across the top, like I'm going left pretty quickly, but y is not changing that fast. But then as I go down, suddenly y starts to change, but x kind of stays the same. And as we go across, we're imagining that happening over time. This is still a little bit abstract, I know, but just trying to point out a difference here, and then it'll start to make more sense once we do some examples. I forget what I wrote under here. Yes, we do this when we're modeling a situation that is changing over time. Sure.
Do you simplify it in any way, or you just leave it as that?
So yeah, it depends on what the problem is asking for. Yeah, so that's a really good point. We're not going to solve this for anything because we actually have 4 different variables now. We have x, y, dx, dt, dy, dt. What we're going to be doing is substituting into that and solving for one of them. So I'm going to add something like that in. So don't solve for anything yet. Then we'll look at the specific examples. So to summarize here, normally what we've been doing all year is we've been taking the derivative with respect to x. X has been our main variable. Now we can take derivatives with respect to t, even when t is not a variable in the actual equation. Right? There's no t in this circle, but we're imagining that a point is going around the circle as time passes. And so that's what related rates is all about. It's relating the rates of change of 2 variables. Okay, so let's do some examples. Let's go to page 19 in the packet. I'm not going to read you all these steps. Don't read them today, read them later. Because I'm going to explain it to you. I don't know if you can see that picture on your packet, but that's Sylvester there. That's his nose. There's Tweety. I've never been able to make that picture out on the packet, but once I put it on my iPad, I can actually see it. So anyways, we're going to draw the situation here. Tweety bird is up here in a birdhouse. It's 24 feet off the ground. Sylvester uses a 26-foot ladder to try and get up there. And what we want to notice here is we're making a right triangle shape. So as he's climbing up the ladder, the dog, Hector, which I never knew that was the dog's name. I guess I didn't watch enough Sylvester and Tweety growing up. Starts pulling the ladder away, pulling the base of the ladder away at a rate of 2 feet per second. And so I'm not good at physics, but this is going to cause one of 2 things to happen, but it doesn't matter which one it causes to happen. Either the ladder is going to slide out from under and it's still going to lean against the pole as it falls. Or I guess if Hector is pulling with enough force, he's going to detach the ladder totally away from the pole and still pull it, but the ladder is still going to be falling either way. So it doesn't matter what's actually happening here, but basically what's happening is you have some part of this triangle that's going that way and another part of it that's going that way. But no matter if it's leaning against the pole, it's still making what kind of shape here? What's that? A triangle. What kind of triangle? A right triangle, yes. And so what we're trying to figure out is if he's pulling this at 2 feet per second, how fast is it falling here? Because it's actually not at 2 feet per second. It's at a different speed, which you might not have known. Okay, so when we're solving a problem like this, we want to draw a picture to try and understand the situation. But the main thing we want to come up with is an equation to represent the situation. This equation is really important. I love its interpretation of my handwriting. It's kind of similar, I guess. Okay. There's a couple different possibilities we need to think through here, but I'm going to write up some of those possibilities, and I want you guys to figure out which would be the best equation to use and why. So you're going to talk about this. Okay, and where I'm getting these letters X, Y, and Z is I'm calling that X, this is Y, and this is Z. Just because it, like, think of X-axis and Y-axis, and then Z is just going to be the hypotenuse. Let's call these A, B, C, and D. So I'm going to tell you which one's the best one in a second, but I want you guys to think through it first. So which of these is going to be the best equation to represent the situation that's happening in this problem here? Talk about it with your neighbor. Okay, raise your hand if you think A is the best. Raise your hand if you think B is the best. Raise your hand if you think C is the best. Raise your hand if you think D is the best. Okay, raise your hand if you thought B was the best. You guys are right. Cav, why is B the best?
Because Z can't change, and otherwise it's just kind of the Pythagorean theorem. Except Z can't be a variable.
Okay. Yes. Yeah, this ladder is not changing heights. It's still 26 feet. It's extended all the way. But are X and Y changing? Yes. X and Y are changing because the ladder is moving that way. It's moving out to the right. It's moving down. But Z is not changing. So we don't want to represent Z with a variable because it's a constant. But we do want to represent X and Y with variables because they are changing. And so that's the main tip here that I have for you guys when you're writing your equations is use variables when something is changing. Use constants for things that are constant. Because in every situation, there's going to be something that's changing and something that's not changing. Or sometimes everything's changing. Those are harder. Okay, so we're going to use equation B here. I'm just going to erase these other ones. All right, so this is our equation. We are going to take the derivative with respect to t. Now this is the exact same derivative that we just saw, because it's going to be 2x dx dt plus 2y dy dt equals 0. Just like we saw in the intro. Okay. Our next step is going to be to substitute into this and solve for whatever it is we're solving for. Okay. So we are looking for how fast is the ladder falling when it's 10 feet off the ground. So we're looking for that speed. Of those variables, which one represents how fast the ladder is falling? Yeah, go ahead. dy dt, yes. So dy dt, that's what we're looking for in this problem. It's not always what we're looking for, but it's the rate of change of the y variable. Okay, so we're going to plug in all the other variables that we know. We know that the ladder at this instant is 10 feet off the ground. That's what it says in the problem. How fast is the ladder falling when it's 10 feet off the ground? So that means y equals 10. Oops. 2 times 10 times dy dt. We know we're going to solve for dy dt, so we don't plug anything there. We have to think about this situation here. If the ladder is 10 feet off the ground, if the hypotenuse is 26, at that instant, what does x equal? How would we figure it out? Yeah. Pythagorean theorem. Yes, exactly. This is still in a right triangle shape. So they still have to fall under this situation right here. Now, this is a multiple, just to make your math a little bit easier, this is a multiple of a 5 and 13 triangle. Do you guys remember what the leg is there? 12 is right, yeah. So x is 24. At this instant, x is 24. Otherwise, you can just do 26 squared, which is 676, minus 100, which is 576, which is 24 squared. So you can do Pythagorean theorem, you're in AP Calculus. So 2 times 24 times dx dt, which is 2. And it's 2 because we're moving to the right, which is our positive direction. When we solve this, we should get a negative number for dy dt because it's falling down. And it will work out to be negative. So now we just solve for dy dt. So we have 24 times 2, which is probably 96, right? 24 times 2 times 2? Yeah, I meant to say 4. Plus 20 dy dt. So we subtract 96. We divide by 20. 96, well, divided by 4. So this would be negative 24 over 5. Did I do that right? Did I math good? 96 over 20, 24 over 5. Is that right? Okay, sweet. So this is dy dt, so this would be feet per second. Or I mean, that's like negative 4.8 feet per second. Either one of those is good. Make sure we have the units in there. Notice it worked out to be negative because it's falling down, but that's because it is keeping the same triangle shape. So if one side's getting longer, the other side has to be getting shorter. And it will work out that way. Yeah, Sarah? dx dt came from this right there. Hector is pulling the pole at 2 feet per second. So one thing with the related rates that I want to point out here is when you first come up with that equation, the equation represents the general situation. So x and y are changing in this situation. Once you take the derivative and you start substituting, then you're going to start thinking about a specific instant in time that we're at. And so that's where we got x and y from, because at the instant that y is 10, x is 24. But you don't want to use 10 and 24, you don't want to plug them into the original equation because they're still changing over time. We plug it in once we take the derivative to find out the speed at that instant. So you do all your substituting into the derivative. That's usually an area of confusion. So I'll continue to talk about that. But I want you guys to take a look at number 2 here. Did you guys ever see those commercials? How many licks does it take to get to the center of Tootsie Pop with the owl? You know what I'm talking about? Some of you guys do, some of you guys don't. Talk about it. Okay, turn to your neighbor. What's the general sort of equation that we want to model this situation? Okay, what equation do we want if it's a spherical Tootsie Pop? Yeah. Okay, do you guys agree? We want the equation of the volume of a sphere. Do we agree? Okay, because that's what's changing, right? We have a sphere, it's losing volume. We also want to know how the radius is. So we don't want to use, Pythagorean theorem, that's not going to help us. We don't want to use volume of a cone, it's not cone-shaped. We want to use volume of a sphere, which is V equals 4/3 pi r cubed. So this is our equation. There's 2 variables in it right now, volume and radius. As we think about the Tootsie Roll Pop, as it's getting smaller, are either of these things, volume or radius, constant in this situation? No, they're both shrinking, right? So this is a little bit different than the one before because in order for the volume to shrink, the radius has to shrink, and that's the only way that this can happen, okay? So this is the equation that I want to take the derivative of because the volume and the radius are both changing. So when we do the derivative of volume, it's just dv dt. This is change in volume over time. And when we do the derivative on the right side, we get 4 pi r squared dr dt. This one is really often forgotten. Don't forget. Whatever variables you're taking the derivative of, you still take the derivative normally using all of our derivative rules. You just put a d whatever dt next to it. So we did power rule. It's r squared now. It was r cubed. We multiplied by 3. That's why the 3's canceled out. But it's still r squared dr dt. dv dt is what? What does it equal? Yes. That's right there. That's our change in volume. And it's negative because it's shrinking. Now, if you did this with a positive number, you would get a positive answer for the radius, and you should just make it negative because you know it's shrinking. Like if you think about the situation, as radius shrinks, volume shrinks. As volume grows, radius grows. It doesn't matter if they're positive or negative. They should just be the same thing. Like just think about the situation. But if we make it negative, our answer is going to be negative. The math is going to work itself out. Just make sure that your answer agrees with the situation. At this moment, what does r equal? Hmm?
0.75 or half of it.
Mm-hmm. Yes. So it's 0.75 divided by 2 times dr dt. So what are we trying to solve for here? Do we know dr dt? No, that's what we're trying to solve for, right? Okay. Now, so if we don't have a calculator here, I would definitely recommend changing all of these to fractions. So that way you have negative 1/4 equals 4 pi times 3/8 squared dr dt. Because 0.75 is 3/4 divided by 2 is 3/8. And so then we're just solving here. So, oops. Negative 1/4 equals 4 pi times 9/64 times dr dt. I would recommend that you reduce as you're solving here. So clear out that 4 and make that 16. That way when you solve, it's just a little bit easier. We're going to multiply by 16/9 pi on both sides. That's going to reduce. So we get 4/9 pi. Negative 4/9 pi equals dr dt. Oops. And it's inches per minute. Questions on that process? Okay, I'm just going to point out again. Notice we didn't plug in this value for the radius until after we'd taken the derivative. That's like the instantaneous value. So the reason we wait is because it's changing. So it needs to be a variable in the original equation. Okay. Let's see. want you guys to do example 6. This is on page 21. I would recommend try to draw the situation, imagine it, see if you can set up the equation. All right, guys, let's check this one. You draw my picture first here.
Yeah, it's like you actually see your
Okay. So we've got our situation here. We've got a rectangular well that's 6 by 4 by 8. We've got water coming in at a rate of 3 feet cubed per second. So what are we talking about here? What kind of formula should we use? What's this situation all about? Volume, yeah. What's volume of a rectangular prism? What's volume of a rectangular prism? Yeah, we could say length times width times height. We could say x times y times z. Okay, which of these are changing in this situation? Just height, right? That's the only one that's a variable. So, what do we want for L? What's L going to be? 6 times 4 times h. So our equation that represents this situation is just this. V equals 24h. Because that 6 and 4 aren't going to change. It's only the height that's going to change. So this is our starting point. When we take the derivative, we get dv dt equals what? Was it?
Oh, 24 dh dt.
Yeah. 24 dh dt. Because like the derivative of h is 1, we just add dh dt. Okay, so these things are kind of like directly changing here because it's a pretty simple derivative because there's only one variable. What is dv dt? 3. So it's just 1 over 8 feet per second. Now, so just to explain the units real quick, this is 3 feet cubed per second. This right here, this 24, this is 6 feet by 4 feet. So when we are dividing by 24, we're dividing by 2 of those feet, which is why we're just left with feet per second. But you don't need to really keep that in mind. You just need to think about like the height is rising. That's all we're measuring. So the height is measured in feet, volume is measured in feet cubed. The math is going to work out that way, but you should know like it's going to be feet per second. Okay, any questions on that? All right, we're going to skip way ahead here. There's a bunch of examples. We're going to do a lot of practice next class. We're going to go all the way to page 25. Page 24, example 12. In the past, I've done these as 2 separate lessons, but I kind of like just doing it as one because the rules are the same. So this is page 24. Example 2. Same deal here. We've got a ladder that's falling. So we can draw that. It's being pulled away from the wall at 2 feet per second. Part A This is the same as what we did earlier with Sylvester and Tweety. Okay, so we're going to skip part A for now. What we're going to look at is, well, actually, no, let's not skip part A because this is new. Part A, well, let's just walk through it together. X squared plus y squared equals what? What should we write? 12 squared, because the ladder's not changing, but x and y are changing. Because this ladder's falling and it's being moved that way. So we have 2x dx dt plus 2y dy dt equals 0. Now we can start thinking about what's happening at these instants. At the instant, it's 6 feet off the ground. Y is 6. X would be 6√3. How do I know that? I do 144 minus 36 is some number, and the square root of that is 6√3. But I know this because I see 6 and 12. So 30, 60, 90, yeah. So that must be 30 degrees. So this is my long leg, 6√3. Yeah. Good old 30, 60, 90s. Okay, so I would plug those numbers in. 2 times 6√3 would be 12√3 times dx dt, which is 2 plus 2 times y times dy dt equals 0. Oh, it's frozen. Why? Okay, so once we take the derivative, we plug our numbers in there. Now we're just solving for dy dt. So I'm going to subtract 24√3 to the other side. And so dy dt equals negative 2√3 feet per second. Okay, that's the same idea as before. What we're going to bring into play now is finding angles and using trig, but it's the same idea. That's the angle of elevation. Throw back to geometry and pre-calculus. So we want to know now, as this ladder falls, what's the rate of change of this angle? Like, obviously it's going to get smaller because the ladder is falling to the ground. What's the rate of change of the angle? So same deal, we need to come up with a situation that represents this equation. This equation there represents the situation, but what's the problem with that equation? It doesn't include theta, it doesn't include the angle. Exactly. It's not going to help us find d theta dt, which is what we're going to be looking for. So there's basically 3 equations that we could use. Well, there's 6 total, but there's 3 main ones: sine, cosine, and tangent. We could say sine of theta, bless you, equals x over 12. Cosine of theta, equals y over 12. Or tangent of theta equals x over y. Why did I switch them? I don't know. Let's just keep everything in line with pre-calc and our unit circle. Okay. I just switched x and y randomly. All 3 of these represent the situation. 2 of them I would use, 1 of them I wouldn't want to use, but would still work. Which one do I not want to use? What am I about to do? once we have our equation, what am I going to do next? Take a derivative. Yeah. Which one of those is going to be the hardest derivative by a mile? Tangent, because I have to use quotient rule. The other ones I don't. Now, I would say cosine is the best one to use because it has x in it, and we were given dx dt. We did just find dy dt, but dx dt was given to us in the equation. So that's why I would argue that cosine is better. But in every problem, you will have a choice of which to pick, and some will be harder than others. But let's go with this one. Derivative of cosine is negative sine theta d theta dt. So we have to do the same thing here. X over 12 is the same thing as 1/12 x. So this is just 1/12 dx dt. Now we substitute. We're solving for d theta dt. I'm just going to write it down on that paper because I'm running out of space. What is sine of theta at this moment? Turn your neighbor. What does sine of theta equal when the ladder is 6 feet off the ground? 6 feet from Cap?
1/2.
1/2. Yes. Theta at this instant is 30 degrees. At this instant, the opposite side is 6. The hypotenuse is 12. 6 over 12 is 1/2. Or if we know it's 30 degrees at that moment, sine of 30 is 1/2. So we're going to substitute 1/2 in right there. So it becomes negative 1/2 times d theta dt, which we don't know, equals 1/12 times dx dt, which we do know, which is 2. And so we just solve. So d theta dt equals 1/6 times negative 2. So negative 1/3. What are the units? Yes. Radians per second. A radian is measuring like a ratio of sides. So the units of theta will always be in radians per second. Not degrees per second, radians per second, always. No matter what side lengths you're using, because radians measure a ratio of sides. If we wanted degrees per second, we would have to multiply this by 180 over pi. Just so you know. So it's the same idea when we're using related rates with trig. It's just you're going to have a choice of which one to pick based on the situation. They all will work. Some will take more work than others. Turn to your neighbor. I want you to recap. Why did we decide cosine is the best? Why is cosine better than sine, and why are sine and cosine better than tangent in this situation? Talk about it. So why was tangent the worst one? We have to use quotient rule. Why is cosine better than sine? Instead of using 2√3, but what's the difference between like dx dt and dy dt in terms of,
We're given dx dt.
Yes, we're given dx dt. So if we hadn't done part A, we would have to do a lot more work to use sine. We did part A first, so we knew it, but just in case we made a mistake, we don't want to carry through our error. So we were given dx dt. Sine would still work just great. The derivative is cosine of theta, d theta dt. And that equals dy dt times 1/12. This is cool. I'm using a little pencil. The cosine at that moment is √3 over 2 times d theta dt. But we have to use dy dt, which was negative 2 √3. times 1/12. It'll still work out to be 1/3 if you math it. But it's just a little more work if we don't know dy dt from the beginning. Okay, so that's a lot of notes today. Next class, we're going to do a lot of examples, and then we'll have the quiz at the end of class.